What if I told you that there was a planet in our solar system so massive, so commanding in its presence, that it behaved more like a failed star than a planet? Enter Jupiter, a behemoth shrouded in swirling storms, crackling with magnetic power and surrounded by a retinue of moons that resembles a miniature planetary system. With 95 confirmed moons in its gravitational grip, including 4 Galilean giants that could be planets in their own right, Jupiter exerts a gravitational influence so vast that it not only shepherds asteroids and comets, but actively shapes the architecture of the entire solar system. Its magnetic field is the largest and most powerful of any planet, extending millions of kilometers into space and creating a deadly radiation belt that dwarfs Earth's Van Allen belts. And orbiting within this realm of titanic forces is Juno, NASA's tenacious robotic emissary, launched to peel back the layers of this enigmatic world and reveal secrets that have eluded astronomers for centuries. Launched in August 2011 from NASA's Kennedy Space Center aboard an Atlas V rocket, the Juno spacecraft began an ambitious journey that would span 5 years and cover a staggering 2.8 billion kilometers through the vastness of space. It wasn't a straight shot. Juno first looped around the inner solar system and in 2013 performed a crucial gravity assist maneuver around Earth that catapulted it towards the outer planets. This complex trajectory allowed Juno to gain enough speed to intercept the gas giant while conserving fuel, a feat of aerospace engineering and orbital mechanics. When Juno finally arrived at Jupiter in July 2016, it was placed in a highly elliptical polar orbit designed to maximize science return while minimizing exposure to Jupiter's intense radiation belts. The original mission plan called for just 35 science orbits, each a daring plunge close to the cloud tops. But the mission proved so successful and the spacecraft so resilient that NASA extended its life twice, bringing the total number of orbits to an impressive 77. Each of these passes, known as perihoves, moments when Juno comes closest to Jupiter's surface, sometimes to within a few thousand kilometers, has served as a new stroke on an ever-evolving portrait of this gas giant. With each close encounter, Juno has peeled back layers of mystery, probing deep beneath the clouds and offering an unprecedented view of a world once thought to be unknowable. Over the past 2 years, Juno has been busy, really busy. One of its most fascinating and challenging targets? Io, the innermost of Jupiter's 4 Galilean moons. This small, tortured world is a volcanic leviathan, so intense in its geological activity that it is redefining what we thought was possible for a planetary body. Unlike any other moon in the solar system, Io is under constant gravitational assault, not only from the colossal pull of Jupiter itself, but also from the rhythmic tugs of its fellow moons, Europa and Ganymede. These interactions stretch and compress Io with relentless force, causing its interior to heat up dramatically through tidal friction. Imagine a rope in a cosmic game of tug-of-war, only the rope is made of rock and the players are planetary giants. This brutal stretching and squeezing isn't just causing stress fractures, it's melting Io's interior. The result? Explosive volcanism on a scale that dwarfs Earth's most dramatic eruptions. Huge plumes of superheated gas and molten rock routinely erupt from Io's surface, rising tens of kilometers into space and forming umbrella-like clouds that linger before raining down sulfur and ash. Thanks to Juno's daring close passes, some as close as 1,500 kilometers from the surface, we now have the most detailed and haunting images of Io's northern polar regions ever taken. For the first time, ghostly plumes rising from volcanic vents near the poles have been observed in silhouette against the blackness of space. As well as being visually stunning, these images are scientifically invaluable, providing clues to the distribution and mechanics of polar volcanism on a world where chaos is the default state. From Loki Patera, a magma lake so vast it could swallow entire nations, to Steeple Mountain, a jagged spire piercing the sky 7 kilometers high like a dagger thrust into the heavens, Io is nothing less than a cosmic furnace sculpted by chaos. The most volcanically active body in the solar system, this tortured moon churns and burns with a fury unlike any other. During its daring flybys, Juno managed to capture 2 volcanic eruptions in real time, dramatic plumes of superheated gas and molten rock shooting up into the dark Jovian sky like glowing geysers. These aren't just spectacular visuals. They are direct glimpses into a moon where the surface is in a constant state of rebirth, with lava flows rapidly erasing the scars of impact before craters can even take hold. With its suite of infrared and microwave sensors, Juno has painstakingly mapped Io's heat patterns, revealing the intricate anatomy of its volcanic activity. This effort has produced the most comprehensive thermal map of Io ever made, a glowing tapestry of hot zones, some transient, some persistent, like the flickering embers of a living, breathing fire. Beyond the known hotspots, Juno has detected tantalizing signatures near the poles, suggesting the existence of previously unknown polar volcanoes shrouded in shadow and cold. And perhaps most intriguingly, deep beneath the cracked and shifting crust, there are hints, just the faintest whispers, of an underground ocean of magma. If confirmed, such a reservoir would rewrite our understanding of Io's internal heat engine and raise new questions about how such a small moon can sustain such furious geological life over billions of years. But let's not forget the giant itself. Jupiter's atmosphere is a wild, churning sea of storms, a dynamic, restless system where cyclones, anticyclones, and jet streams interact in a ballet of chaos and beauty. These storms aren't just meteorological curiosities. They are expressions of deep, underlying atmospheric processes that extend far below the cloud tops. Some of these monstrous storms are so huge they could swallow the Earth whole, their winds howling at speeds of over 600 kilometers per hour. Thanks to Juno's powerful microwave radiometer, MWR, we now have an unprecedented window into what lies beneath the planet's iconic striped cloud bands. Rather than shallow weather systems like those on Earth, Jupiter's storms are monumental columns of energy that reach hundreds of kilometers deep. Some of the polar cyclones dig so deep, more than 100 kilometers below the cloud tops, that they can connect to deeper layers of the atmosphere, acting as conduits for the transfer of energy and matter. Others are surprisingly shallow, suggesting a great diversity in storm structure that defies simple classification. Then there's the central cyclone at Jupiter's North Pole, so striking and symmetrical in visible and infrared images that it almost resembles a cosmic flower. But in microwave wavelengths, it almost disappears, as if shrouded by an invisible veil. This stark contrast suggests a fundamentally different composition or thermal structure beneath the surface and raises new questions about how such storms form, evolve, and persist in Jupiter's turbulent atmosphere. Between its 61st and 66th orbits, Juno captured some of the most fascinating and scientifically valuable images yet of Jupiter's enigmatic filamentary region, a transitional zone where order dissolves into chaos. Here, the gas giant's iconic stripes, normally so well defined, begin to blur and twist into vast, turbulent vortices. These storms appear like swirling eddies in a cosmic ocean, some stretching thousands of kilometers across, forming and dissolving in a mesmerizing dance. It's a region of atmospheric instability where the predictable becomes unpredictable, governed by fluid dynamics that we are only beginning to understand. In these images, it's like watching an alien atmosphere breathe, undulate, and ripple, a storm system larger than Earth itself, animated by a rhythm that defies simple explanation. Scientists believe that these swirling features may hold clues to the transfer of energy and momentum in Jupiter's atmosphere, and perhaps even to weather patterns on exoplanets with similarly thick gaseous envelopes. Juno even caught a fleeting but fascinating glimpse of Amalthea, one of Jupiter's more elusive moons. This tiny potato-shaped moon is only 84 kilometers across, but its surface glows with an intense reddish hue, making it the most crimson object in the entire solar system. Scientists think the color may be due to sulfur compounds or complex organic matter, but there's another mystery. Amalthea appears to be warmer than expected for such a small, distant moon. Could it be heated internally by the tidal pull of Jupiter's gravity? Or could electrical currents flowing through Jupiter's strong magnetic field be generating heat from within? The exact mechanism remains uncertain, but these tantalizing clues suggest that there's more going on beneath its oddly shaped surface than meets the eye. Then there's the question of water, perhaps the most pressing mystery of all when it comes to Jupiter's inner workings. Juno is playing a key role in answering a question that has puzzled astronomers for decades. How much water does the gas giant actually contain? Using its microwave radiometer, MWR, Juno has peered deep beneath Jupiter's thick clouds and revealed a surprising revelation. Water vapor is present, and it's much more abundant at the equator than previously thought, possibly 3 to 4 times more than we observe on the Sun. But here's the paradox. While the upper atmosphere appears to be rich in water, Jupiter's core appears puzzlingly dry. This unexpected dryness contradicts models of planet formation, which predict a wet, icy origin. Could Jupiter have formed in a drier region of the early solar nebula? Or did intense internal mixing redistribute water unevenly over billions of years? The answers could revolutionize our understanding of how not only Jupiter, but all gas giants, and by extension the architecture of our entire solar system, came to be. We're now entering the final breathtaking chapter of Juno's epic odyssey. Only 8 orbits remain before the spacecraft comes to a dramatic end in September 2025. In a deliberate, fiery descent into Jupiter's atmosphere, Juno will self-destruct, a heroic act to avoid any possibility of contaminating Jupiter's moons, particularly Europa, which may harbor the ingredients for life. This final maneuver, though somber, is a testament to the mission's deep respect for the sanctity of celestial bodies. Until that last fiery breath, Juno continues to work tirelessly, delivering scientific riches from the edge of our solar system. Each orbit brings new wonders, stunning images of auroras dancing across Jupiter's poles, detailed thermal maps of volcanic eruptions on Io, and atmospheric data that challenge what we thought we knew about gas giants. With each packet of data beamed back over millions of kilometers, Juno writes another line in a love letter to exploration, curiosity, and the boundless unknown. So, what do you think? Could Io's internal heat be more than tidal friction? Perhaps a deep planetary magma ocean? And what about Jupiter's puzzlingly dry core? Is it a random anomaly or the missing piece of our solar system's origin story? Let me know your thoughts in the comments below. I read and appreciate every one of them. If this kind of cosmic storytelling sparks your imagination, don't forget to subscribe and tap the notification bell. There's a universe of stories waiting to be told, and we're just getting started. See you on the next orbit. The adventure continues.